Today what we're going to look at is wave superposition and interference. We're going to once again review and describe the difference in position between two waves using the terminology phase difference. And we're going to then predict the type of interference from the phase difference between the waves. Sounds more complicated than it is. Let's review first what phase difference means. Phase difference is a way to compare two waves. We use radians, where 2 pi radians represents a full circle, in the same way that it will also represent a full wave. Earlier on in the topic, we did a comparison. We looked at how a motion in a circle is equivalent to the motion in simple harmonic motion. So, we can use this circle analogy as a way of describing the difference between two waves. This means that there are 2 pi radians in a full circle, and so there's 2 pi radians in a full cycle, in a full wave. Similarly, pi would be equal to half a circle, or half a wave, and then pi over 2 would be the quarter. Let me just change that of a circle. So phase difference is the difference in the fraction of the wave cycle that has elapsed relative to the origin or some other fixed point. So if we have a look at some of these videos, here we can see that all of these pendulums have a phase difference. That means they're all out of sync with each other. And that phase difference, in fact, is constantly changing. And that's why their difference in the cycle is increasing. Now that was in oscillations. Now that's when we're talking about different waves, we basically mean that they go through the same equilibrium position at the same time always when that phase difference is 0. So here we can see a bunch of waves that have 0 phase difference. They're actually in phase with each other. That means they all go through the equilibrium position, which is in the center here, at the same time. And this is a diagram of two oscillators which have a phase difference of pi over 2. Now, 2 pi is equal to 1 cycle. Pi is equal to half of a cycle. So pi over 2 is a quarter of a cycle. Now let's have a look at what that means on this diagram. The red one is going through the equilibrium position at time equals 0. An entire cycle would be from there to here, right? A quarter of that would be the equivalent of this section here. Okay, so by saying that the blue wave is out of phase by pi over 2, is that a quarter of its cycle is out of sync with the red one. Now the best way to think about this mathematically is to think about time. The period of this one from here to here, if we use that, a quarter of that entire period is the time it will take the blue one to catch up. So that means that t over 4, which would bring us to here, at that point, the blue oscillator is reaching equilibrium. T over 4 later, and that will be the same everywhere. If the red one reaches its peak at this point, the blue one will get there t over 4 later. So it's behind by a quarter of a cycle. I hope that made sense. Here we have two oscillators that have a phase difference of pi. Now that's a half of a cycle. So in the same here we have the blue line, it's reaching equilibrium at this point. I think we should start our explanation here because that's when they're both together. Now let's have a think. Let's look at the red one, first. The red one at 180. Let's have a look at the period of this one, we actually have some numbers. So from 180 to 550, that's the period of this wave. The blue wave will arrive at this point, the equilibrium, half of that period later, right? So here we are. This is our t over 2 point, and that's when the blue one arrives at this point. And it's important that you see that arriving at this point means that the behavior is the same. The red one starts at equilibrium and goes up. The blue one starts t over 2 later and goes up. There. So where are we going with this? Because this is all review. Well, let's have a look at that relationship between phase and interference. We have to think about waves meeting each other now. So the whole point of this is to predict what will happen when two waves meet. Now for that, I'd like you to look at this rather hypnotic situation. I'll bring it back to the beginning, where two waves hit each other and produce this kind of weird rippling effect. Now, what you should notice is, as a consequence of these two radial waves, what we end up with are these kind of peaks, these areas where the waves are really clear, and then some areas where there's just nothing. So let me show you here. We can see, oops, start that again. Let's have a look. We can see that there are areas of consistent motion and areas where there's nothing. Like here, you should be able to see that there's all this area of like no displacement at all, right? Same here, no displacement. Here, no displacement. Yet there are other areas where these nice waves form. So in terms of interference, this interference has some really weird effects, specifically on the amplitude of the final wave. So if we have a look at some waves that are interfering with each other, here we have two radial waves. You can see that the consequence is definitely on the amplitude, and it's not there's no overall consequence. There's actually a real diversity of situations. But what I want you to notice is these areas here where actually the amplitude's 0. Let me show you that again. Okay, there is our two waves interfering with each other, and you get some areas where the amplitude pretty much just stays where it is over here. So you can see these areas here, here, and here, where the waves are literally cancelling each other out. And then there's other waves where you get some really strong waves forming, right? So that effect of two waves coming together and affecting each other's amplitude is called superposition. This is its fancy definition. Okay, I've got a visitor, hang on. So here's our official definition. The principle of superposition states that at any moment, the overall displacement at a point will be the vector sum of all the individual wave displacements. You can see here that we have an example of this, of these ducks trailing behind. This duck at the back is definitely in for a really bumpy ride, as it's experiencing the waves coming from this duck superimposed with the waves coming from this duck. So in effect, he's going to get this kind of like extra amplitude to his vibration. So the amplitudes reaching this duck are going to be the vector sum of the individual waves coming from this one and this one, and possibly maybe even some of that one. Let's have another look at what happens when these waves come together. This is an example from a ripple tank. A ripple tank is a really old-fashioned piece of physics lab equipment where you can actually just see these little water waves in a thin tray of water. Now, we're actually looking at diffraction effects as well, because these water ripples, these radial water waves that are coming across, are actually happening because of diffraction effects. There's a gap. Okay, so what we're going to have a look at is what happens when you get two wave sources interfering with each other. And I'll just show you. You can see here are our two waves. And once again, this is what we saw in the last video. You're getting these areas where there's something happening to the amplitude. Here, for example, this is an area where the amplitude is actually 0. So what's going on with that? Well, there are two types or two extreme cases of interference or superposition. The first one we're going to look at is destructive interference, which is representative of those areas where the amplitude is 0. Destructive interference happens when the waves superimpose, when they add up to give you 0, right? So have a think, what kind of phase difference can you see between these two waves, right? They're basically out of phase by half a cycle, which is pi, right? So if there is pi difference, then you would say that they were destructively interfering. The other extreme case is where you have constructive interference. This is where the amplitudes add up to give you a massive amplitude, right? So your vector addition increases the amplitude, and that's when the waves have a phase difference of 0, right? They're in line with each other. Okay, so constructive interference is when the waves superimpose to create a larger oscillation, and destructive interference is when the waves superimpose to create a smaller oscillation. And these two situations of a path difference of either 0 or pi are extreme cases. Quick exercise that you can do to try and see if you've understood everything so far. Here we have two waves, right? They're actually very different to each other, but I want you to demonstrate that you understand what superposition means by sketching out a wave or the final wave if these two waves add onto each other, right? So stop the video and actually sketch out a third graph showing me the amplitude of these two waves together. So I'll start it off for you. At time equals 0, the amplitude would be 0 of this third wave, the resultant wave. But at this time point, we have a positive displacement up here, and here we have a positive displacement up here. So that means that our total amplitude would be this plus this. So it would be something like that. The wave would go up to there. So I want you to do that with all the points and see what you get as your graph, and then take a picture and post it on Classroom for me. So that is the main skill, and the three big takeaways for this section are your definitions. You definitely need to start learning some definitions off by heart. So for this section specifically, constructive, destructive interference, and superposition.